Okay, so let's talk about degree sequences. So, um, this is about section 1.7. And I've already kind of talked a little bit about what degree sequences are, but just to remind you, the degree sequence is of a graph is it's just a sequence of numbers representing all the degrees of all the vertices. So this graph has this degree sequence because this vertex has degree 4, this one has 3, and then there's 3 different vertices with degree 2. There's this one, and this one, and then there's a vertex of degree 1, and that's all the vertices, so they're all represented here. The standard way to write a degree sequence is in non-increasing order. Of course, you might have several copies of the same number, but you can arrange it so that each one is greater than or equal to the one that comes after it. But formally, we're not going to demand that of a degree sequence. So I would also say that this graph has this degree sequence. It's just the same numbers in a different order. You've got 3 2s, you've got a 1, a 3, and a 4. So what we're going to explore today is which sequences are the degree sequence of a graph. And it's not every sequence. Just because you come up with a sequence of numbers doesn't mean that that sequence is the degree sequence of any graph. There might not exist any graph with the degree sequence that you come up with. So we say that a sequence is graphical if there is a graph whose degree sequence is that. So we're gonna investigate which sequences are graphical today. So just to get past, because initially this might come off as a weird question, but so just to convince you that not all sequences really are graphical. For example, here's an example of a non-graphical sequence. This one is really badly non-graphical. First of all, well, there's two easy reasons why this can't be the degree sequence of a graph. The first reason I'll touch on is that the sum of the degrees is an odd number. And as we've talked about before, if you add up the degrees of any graph, that's supposed to be 2 times the number of edges, so it should always be an even number. But if I add these up, I get 105, which is an odd number. If the sum is odd, then it can't be graphical. There's another reason why this isn't graphical. It has a number that's way too big, basically. So if this were the degree sequence of a graph, it would have 5 vertices, 1, 2, 3, 4, 5. So how could you have a vertex whose degree is 100? The largest possible degree of a vertex is if it was adjacent to all the other vertices, right? A vertex can't be adjacent to itself, but it can be adjacent to every other vertex. So in a 5 vertex graph, the largest possible degree would be 4. If it's just adjacent to everything else, then its degree would be 4. There's no way to even come close to 100. So this is definitely not graphical. But there's more subtle reasons why a sequence may not be graphical. For example, this one. So I'm telling you, this is not graphical, but it isn't for either of the reasons that we covered on the first one. So first of all, if I add up the numbers, I do get an even number. So I can't say immediately that this is non-graphical just because the sum is odd, because it's not, it's even. Also, it is possible to have a vertex of degree 4. So, I don't see a vertex whose degree is just too big, right? This is a 5 vertex graph, so it really could have a vertex of degree 4. And actually, it might be a good time to just pause the video and think for a second about why this isn't graphical. But, so assuming you did that, I'll just tell you why now. let's think about this again. Like I said, this graph, it is possible for a graph with 5 vertices to have a vertex of degree 4. But the only way is if that vertex is adjacent to everything else. But here I have a vertex that's supposed to have degree 0. So how can I have this vertex that's adjacent to everything and this vertex that's adjacent to nothing? That can't be. That's why this is non-graphical. Let's talk about C. C is kind of similar, but it's slightly more subtle even than B. Okay, so, whoops, actually, yeah, okay. So as written, actually, this is very easy because the sum is odd. I didn't mean to do that. Let me fix this. Let me change this 3 to a 2. Okay, that's better. Now this is not so easy. I'm telling you that this sequence is still not graphical, but the reason isn't so easy. So once again, if you check the degree sum, it's even. So now that I fixed it, of course. Also, we can think about the fact that this is a 5-vertex graph, so we are allowed to have vertices of degree 4. That's the largest degree we could have. And I can't use the same argument that I used last time, right? Because I don't have a vertex of degree 0. So what am I going to say this time? Well, this vertex needs to be adjacent to everything. This vertex also needs to be adjacent to everything else. So then how can I have a vertex of degree 1? Right? Every vertex in this whole graph needs to be adjacent to this one and this one. So every vertex would have to have degree at least 2. So that's why this one is not graphical. So right, of course, these tricks that we use to solve A, B, and C, they're kind of particular where you have to carefully look at the sequence and come up with a reason. But we would like to have a general sort of procedure or method to tell whether a sequence is graphical. So let me embark on that. So here's an idea. This is an operation we can do on a graph to make a different graph. The operation is called a two-switch. And basically the operation is like this picture. So imagine that, and that you'll hopefully get used to me drawing sort of abstract graphs. So imagine that there's a graph. Like I'm not really telling you that there's only 4 vertices. There might be more vertices here and more edges that I'm just not drawing. So imagine that there's a graph, but it contains 4 vertices, and there's 2 edges like this and this, and when I draw a dotted edge, that's indicating that this edge is not there, and this edge is not there. This may or may not be an edge, this may or may not be an edge. All I'm saying is that we have 4 vertices, this definitely is an edge, this definitely is, this definitely isn't, and this definitely isn't. And what you do to make a new graph is you take this graph, and I'm going to keep everything else the same, because remember, there might be more stuff going on. There might be more vertices and more edges. I'm going to keep all that stuff the same. The only thing I'm going to do is I'm going to remove this edge, and I'm going to put in this edge and this edge. So then basically these 4 vertices will now look like this, and everything else about the graph is the same. For concrete example, I drew this graph, and let me indicate what two-switch I'm doing. And this is like how I was saying, like a two switch is kind of like all the action is on these four vertices, but then there might be more vertices around. So let me tell you which four vertices I'm going to do. Oops, pen doesn't work so well. Okay, there we go. These four. And it basically looks like the picture. I've got four vertices. I've got two of them are adjacent with an edge. And then if I look at the other two, those are also adjacent. I don't have an edge like this, and I also don't have an edge like this. So this is suitable. This is a suitable set of four vertices to apply a two switch to. And then what's it going to look like? Well, basically now this edge will be gone, this edge will be gone, this edge will now be there, and this edge will now be there. So I drew this picture, and I made a little mistake. I need to get some white out, but I couldn't find any in the office today, so sorry for messing it up a little bit. This edge should not be there, right? This was one of the edges that it was there before and should have been removed. So this edge is not there, this edge is not there, this edge is there, this edge is there. All the other stuff about the graph is the same. Of course, I could now do another two switch to get another graph. So you can do sequences of two switches. By the way, if I did a two switch and then I did it again, then I would get back the original picture. Because really the important thing about a two switch is you've got two edges that don't touch each other, and then these cross edges that are not present. And if I were to do that operation again to this, I would get back to this picture. And why are we talking about two switches in the context of degree sequences? Well, it's because if you apply this operation, the new graph has the same degree sequence as the old graph. Right, and in fact, corresponding vertices have the same corresponding degree. Let me take this vertex. This vertex had degree 4, and then this vertex still has degree 4. Even though it's not the same neighbors, like in the first graph, this one had the neighbor in the lower left, and in this one, this vertex does not have the neighbor in the lower left, but the degree is still the same. The degree is still 4. And why is that? That's basically because the only thing that you change is on these four vertices, and you're basically, if you look at these four vertices, when I remove this edge, for example, that's going to decrease the degree of this one. But then I put in this edge, and that makes the degree back the same as what it was. And that happens to all four of these vertices. The edges move around, but the degrees stay the same. All right. So let's have a theorem. This is theorem 1.10 in the book. Let a sequence S consisting of the numbers d1 through dn be graphical. And let's assume that it's in this standard form. It's in this non-increasing form. So d1 is greater than or equal to d2 and so on. And capital delta is going to be another name for d1. It's the largest degree of any vertex in the graph. And then we're going to let fancy G, in the book there's this script G, and I can't, my hands just won't make that fancy looking of a G, so this is my version of a fancy G. So fancy G sub S is the set of graphs with this set of vertices So I just want to name to give specific names to the vertices in G. So I call them V1 through Vn, and we're going to assume that the graph has this degree sequence S, and in particular, the degree of V1 is D1, the degree of V2 is D2, and so on. So the degree of VI is DI. Then what the theorem is saying is that every graph H in this set, the set of graphs that have this set of vertices and the degree sequence S, every such graph can be transformed into a special graph that's in G sub S. And what's special about this graph, G? What's special is in G, the neighborhood of the vertex V1, and by the way, when you're having a conversation about many different graphs and you have to talk about the neighborhood of a vertex, sometimes it helps to specify which graph you're talking about. So this just means the neighborhood in the graph G of the vertex V1. And what's special about G is that that neighborhood consists of basically the next delta vertices. So it consists of V2, V3, V4, all the way up to V sub delta plus 1. In other words, if you look at the subscripts of the vertices, they're kind of in a natural order. The first one's V1, the second one's V2. And what this is saying is that the neighbors of V1 in this graph G, they are like in a consecutive block, and they're the vertices that immediately come after V1 in this ordering. And what is, okay, so once again, every graph H in G sub S can be transformed into a special graph G, like I just described, using some sequence of two-switch operations. And when I say a sequence of two-switch operations, I mean you're allowed to do a two-switch and then do another two-switch and another two-switch, to possibly getting many different graphs that way. And from some sequence of two switches, it's possible to get from H to G. So before I go and prove it, let me show you an example. And this is sort of going back to, I mean, this original graph that I showed you the degree sequence of when I was just defining a degree sequences. This is just that same graph. I labeled the vertices V1 through V6, because I guess there's 6 of them, and I labeled them in a way that's compatible with the theorem. So V1 has the highest degree, and then V2 has the next highest degree. Of course, V3, V4, and V5 all have degree 2, so they could have gone in any order, but I just kind of picked one and called it V3, and so that part was arbitrary, but this is a suitable labeling of the vertices. And you'll notice that this graph is not of the special kind that I described. In other words, the neighbors of V1, because what makes it special? A graph has this property that I'm calling specialness if the degree of V1 the neighborhood of V1 consists of the next block of vertices starting at V2, V3, V4, and it's adjacent to all of them up to a certain point, and then that is its neighborhood. And that's not really the case. V1 is adjacent to V2, V3, okay, good so far, but not V4. And then it's adjacent to V5 and V6. So they're not, like, the neighbors of V1 are not all together in a consecutive block. It goes V2, V3, and then it skips V4 and then goes right to V5. So this one, even though this graph does have this degree sequence, this graph doesn't have the special property of this degree sequence. However, I can take this graph and do a 2-switch, and oh boy, what 2-switch did I do? I did a 2-switch on this set of 4 vertices. 1, 2, 3, 4. Right? I have this edge, I have this edge, I do not have this edge, and I do not have this edge. So this is a suitable set of 4 vertices to apply a 2-switch to. And if I apply that 2-switch, what's going to happen? This edge will no longer be there. This edge will no longer be there. This edge that wasn't there before will now be there, and this edge that wasn't there before will now be there. And this one, once again, has the same degree sequence, and that's not a surprise. When you apply a 2-switch, you always get back the same degree sequence. And this one is special. What's the neighborhood of V1? It's V2, V3, V4, V5, done. They're in a block. They're in a consecutive block, starting at V2 and then going to the next vertex and the next vertex and the next vertex until you're done, and that's all the neighbors of V1. Of course, V1 is not adjacent to V6, but the point is that all of the neighbors that V1 has, they're in a consecutive block, starting at V2. So of course this example isn't a proof. I just wanted to show you on a particular graph. So let's do the proof. So this is a proof by contradiction. I'm going to let W be this set, and really this is the set. Basically, like I want to show that there's a graph G where the neighborhood of V1 is exactly this. This is, once again, what I've been describing as a consecutive block of vertices starting at V2, and where the total number of them is delta. Okay. Among all graphs, okay, let me start over. Imagine starting with H, and once again, going back to the theorem, we're assuming that H is just a graph with degree sequence S. G sub S is like it's the family of graphs with this vertex set and degree sequence S. And I want to show that I can start with H and end up with a special graph G with a sequence of 2 switches. So what I'm going to do is I'm going to imagine every possible graph that I can obtain by starting with H and then applying any sequence of 2 switches. So start with H, apply any 2 switch, and then you're allowed to apply any 2 switch to that, and any 2 switch to that, and keep going and consider all of the graphs that you can ever get that way. And out of all of those graphs, among all of those graphs, I'm going to let G be one of them such that the sum of the subscripts in the neighborhood of G is minimum. So let's talk about what that means. In this graph, the sum of the subscripts of the neighbors in V1 well, so what are the neighbors? It's V2, V3, V5, V6. So the sum of the subscripts is 2 plus 3 plus 5 plus 6, because once again, the neighbors were V2, V3, V5, and V6. And that's whatever it is. I guess it's 16. Of course, if I were to look up here and do the sum of the subscripts, well, now that when it's special, it's kind of an easy organized sum to do, because it's just going to be 2 plus 3 plus 4 plus 5. They're consecutive and they're in a block. And that's 14. And so the idea is that we would like the sum of the subscripts to be small. And so we are choosing a graph that's obtainable from H such that the sum of the subscripts is a minimum. Okay, so we're here. Since this is a proof by contradiction, we're assuming that it's not possible to get from H to a graph with the special property where the neighborhood of V1 is in a consecutive block like this. We're assuming that it's not possible to get from H to any such graph. So G must not have that special property. So in other words, the neighborhood in G of V1 is not W. If the neighborhood of V1 were this W, then that would be the special property that we're looking for. So, but this is a proof by contradiction, so we assume that it's not. So what does this look like? Here, I drew a picture. The neighbors of V1 are not in a consecutive block starting at V2. What does that mean? That means that the neighbors are, we could say, there's a gap. They're not in a consecutive block starting at V2. In other words, this is going back to the example. This one did not have the special property, and so it goes V2, V3, and then it skips V4, and then there's more neighbors. So it skips something, and then there's more. In other words, there's a vertex that isn't a neighbor of V1, and then a vertex that comes after that is a neighbor of V1. In other words, there's a vertex we can call VK, a vertex that we can call VJ that isn't a neighbor of V1, and then another vertex that comes after VJ, so J is smaller than K, that is a neighbor of V1. So I have a picture like this. We have something that isn't an edge, and then something that is an edge, and J is less than K. And of course, remember that we put these degrees in non-increasing order. So if J is smaller than K, that means DJ is greater than or equal to DK. Okay. So we have this, and again, this is an abstract drawing of a graph. So there may be more vertices that I'm not drawing here. I'm just saying that we have 3 vertices that look like this. So next, I claim that there's a 4th vertex that's adjacent to VJ, but not VK. So let me talk about why that is. Well, the degree of VK is this, and that's less than or equal to the degree of VJ. So VK has some neighbors, and VJ has some neighbors. DJ, one more time. VJ has at least as many neighbors as VK, because DJ is greater than or equal to DK. Also, we already know what one of the neighbors of VK is. So um, there's no way, like, if I draw, when I draw something that looks like this, I'm drawing the neighborhood of Vj. I'm saying that Vj is adjacent to all of these. Now, if Vk was also adjacent to all of these, then the degree of Vk would be larger than the degree of Vj, right? Because the number of neighbors would be all of these plus 1. But that's not the case, right? The degree of Vk is actually less than or equal to the degree of Vj. So it can't be the case that Vj is adjacent to all of these. In other words, there's one of these here that isn't adjacent to Vk. That's what we can call VL. So maybe I'll call this one VL. And so we have this edge, and we have this is not an edge. So what do we have here? We have a situation where we can apply a 2-switch on these 4 vertices. Actually, let me even redraw this a little bit, because I've got V1, VK, VJ, and VL. And I have an edge from V1 to VK. I have an edge from VJ to VL. I don't have an edge from VJ to V1, and I don't have an edge from VK to VL. It's the same picture, I just drew it more so that it looks like a 2-switch. So we're going to apply a 2-switch, meaning that I can, put this edge, remove this one, remove this one. So by applying a 2-switch on these 4 vertices, we obtain a new graph with the same degree sequence. And the sum of the subscripts of the neighbors of V1 is smaller. Let's say, okay, let's call the new graph G prime. After I've done the 2-switch to G, I'll call the new graph G prime. So, and what I'm saying is that the sum of the subscripts in this, the neighborhood in G prime, this is like I was telling you, when there's multiple graphs in question, it helps to put a subscript if you're talking about the neighborhood in a particular graph. And in this case, I'm talking about the neighborhood in G prime. The sum of the subscripts in G prime of the name, let me start over. The sum of the subscripts of the neighbors of V1 in the graph G prime is smaller than that in here. Let me explain. Well, when I apply this 2-switch, basically what happens to the neighbor of V1 is when I apply this 2-switch, V1 had VK as a neighbor, and it's not going to have that anymore. Instead, it's going to have VJ as a neighbor. But J is less than K. So if I look at the sum of the subscripts of the neighbors of V1, that sum had a k in it, and we're going to remove that k and put in a j, which is a smaller number. So the sum of the subscripts of the neighbors of V1 is going to be smaller after the 2 switch. And that's a contradiction because how did we choose G? We chose G to be, out of all of the graphs that can be obtained from H using any sequence of 2 switches, we chose G to be the one where the sum of the subscripts of the neighbors of V1 would be as small as possible. So it's a contradiction, the fact that we were able to apply a 2 switch and get something even smaller. All right, so let me cut this video off and make a new one.